Okay, I ended that last video very abruptly, but it's because I wanted to go ahead and start a new video so I could make some shorter ones. Anyway, let's look at how I can find asymptotes and intercepts of rational functions. If I want to find vertical asymptotes, notice that my vertical asymptotes are going to be the places are going to be at the places where my denominator is undefined. It's going to be those places that basically cause me to divide by zero. With one exception, there is going to be one exception. A vertical asymptote will occur whenever the denominator is undefined. So this rational function is going to be undefined anywhere that my denominator is zero, right? So maybe it's better for us to say whenever the denominator is zero, because this is when the function is undefined, right? So let's find the vertical asymptotes of the function k of x is equal to 5 plus 2x squared divided by 2 minus x squared. If I want to find the vertical asymptotes here, I just set the denominator equal to 0. I set my denominator equal to 0 because this will tell me where my undefined stuff is. Now, I don't like factoring stuff that has a negative leading coefficient. So what I like to do is I like to multiply both sides by -1. If you can go ahead and factor this, more power to you. So I'm going to multiply through by -1, and once I do that, I'm just going to rearrange this. So this is x squared plus x minus 2 equals 0 times -1 is still 0. Now I need two numbers that multiply to get -2 that add to get 1, and these are going to be 2 and -1. Here I get x equals -2 and x equals +1. These are where my vertical asymptotes are. These are my vertical asymptotes. Easy peasy. Let's look at another example. Let's find the vertical asymptotes of the function k of x is equal to x minus 2 divided by x squared minus 4. If I just take the denominator and I set it equal to 0, x squared minus 4 is 0, x squared is equal to 4, I get x is plus or minus 2, right? Or I can put this as a list. X is -2, x is +2. However, notice that this function is also equal to 0 when x is 2, right? If I plug 2 in here, I get 0 in the denominator, right? Or in the numerator, rather. Sorry. Because of this, I have 0 divided by 0 when x is equal to 2. And this will actually not cause me to have a vertical asymptote at x equals 2. It will instead cause me to have a hole in the graph. So my only vertical asymptote here is at x equals -2. At x equals 2, I have what we're going to call a hole instead. It's just a single point where this graph is undefined that we're going to indicate with an open circle. Let's get some definitions here. So the vertical asymptotes of a rational function will occur where the denominator of the function is equal to 0 and the numerator is not 0. A hole occurs in the graph of a rational function if an input causes both the numerator and the denominator to be 0. In this case, we factor the numerator and denominator and we simplify. If the simplified expression still has a 0 in the denominator at the original input, then the original function has a vertical asymptote at that input. Otherwise, it has a hole. Oh, this is for horizontal asymptotes. Sorry, I didn't rearrange that properly. Now, for horizontal asymptotes, there are going to be 3 cases. We're going to look at the 3 cases for horizontal asymptotes and how we can find these, right? So I should really title this Finding Horizontal Asymptotes. Case 1. There are 3 different possibilities here. I'll put this one at the end. Case 1 is where, so to find a horizontal asymptote, I have to compare the degree of my numerator to the degree of my denominator. And how those things compare to one another determines if I have a horizontal asymptote and what my horizontal asymptote is if I do have a horizontal asymptote. So case 1 here is the degree of the denominator is greater than the degree of the numerator. So notice here that I have an x squared term in my denominator. In my numerator, I only have an x to the first term. So because the degree of the denominator is greater than the degree of the numerator, the long run behavior of this function, and when we're talking about long run behavior, we're really talking about the stuff that is causing, that's having the greatest effect on the shape of the function overall. If I were to plug in super large values, really this +2 in the numerator isn't going to be doing much to the shape of this graph if I'm plugging in like values that are in the millions or billions or trillions, right? Or even larger. Really the only thing that has effect on the shape of the graph in the numerator is the 3x portion, in the long run that is. And similarly, in the denominator, if I'm looking at really large values, this +4x minus 5 stuff does almost nothing to the shape of the graph in the long run compared to this x squared part. This x squared part has a much larger effect on the shape of this graph. So this means that in the long run, this function behaves as if it were just 3x over x squared, which simplifies to 3 over x. This tells me that as my inputs get very large, because I'm dividing 3 by an extremely large number as these inputs grow extremely large, that my outputs get extremely small. This means I have a horizontal asymptote at y equals 0. Since I'm dividing by a larger and larger number here, as x approaches positive or negative infinity, my f of x is just going to approach 0. In case 2, the degree of the denominator is less than the degree of the numerator. Here, notice that my long run behavior is really f of x in the long run behaves similarly to 3x squared over x, because this is the stuff that has the greatest effect on the shape of the graph. And this is just 3x. Notice that if I plug in arbitrarily large positive or negative values for x, that my outputs grow arbitrarily large in the positive or negative direction. They never level off. In other words, as x approaches positive or negative infinity, f of x here approaches positive or negative infinity. This means that if the degree of the numerator is greater than the degree of the denominator, I have no horizontal asymptote, because the function will never level off at a y value. And I have case 3 here. What if the degree of the numerator is equal to the degree of the denominator? For example, in this example here, well, the long run behavior of this graph is that this function behaves similarly to 3x squared over x squared in the long run. And this simplifies to just 3. This tells me that as my inputs grow large in the positive or negative direction, my function behaves like the function f of x equals 3, which is just a horizontal line. That means that in this particular case, I'm going to say in this particular case, now this is not the case for everything, but in this particular case, I have a horizontal asymptote at y equals 3. Now, it's not always going to be 3 if the degree of the denominator is equal to the degree of the numerator. Instead, notice that this is actually the ratio of the leading coefficients. So if the degree of the denominator is equal to the degree of the numerator, I have a horizontal asymptote at y equals the ratio of the leading coefficients. And next up we just have a chart that has all of these in it, right? This is exactly what we just talked about. If the degree of the denominator is greater than the degree of the numerator, horizontal asymptote at y equals 0. If the degree of the denominator is less than the degree of the numerator, no horizontal asymptote. If the degree of the denominator is equal to the degree of the numerator, horizontal asymptote is at the ratio of the leading coefficients. Let's look at this one. In that sugar concentration problem from before, we created this equation. Let's find the horizontal asymptote and interpret it in the context of this scenario. So here, the degree of the numerator is equal to the degree of the denominator. I have just a t to the first in both the numerator and the denominator. This means that my horizontal asymptote here is at the ratio of the leading coefficients which is at, let's see, the leading coefficient of the numerator is 1. The number next to the t is 1, right? Because I don't see a number there. Divided by the leading coefficient of the denominator is 10. So this particular rational function has a horizontal asymptote at y equals 1 over 10. This tells us that let me make this text larger. The concentration of sugar in the tank will approach 1/10 of a pound of sugar per gallon of water. Or we could think of this as 1 pound of sugar per 10 gallons of water. That's how we would interpret this horizontal asymptote. But it will never quite reach that exact number. It will just get closer and closer to it over time. Let's look at another example. Find the vertical and horizontal asymptotes of the function x minus 2 times x plus 3 times x minus divided by x minus 1 times x plus 2 times x minus 5. So the first thing is we want to see does anything cancel? If anything cancels, I might have a hole. In this case, no, nothing cancels, right? This is actually factored for us, which is very nice. So let's see. Maybe we'll go ahead and find the horizontal asymptote. This is probably easiest. Well, actually, they're both pretty easy in this example. Well, the degree of the numerator, I have two terms that are both linear. I'm multiplying them by each other. If I want to find the horizontal asymptote, I need to find what the degree of the numerator and degree of denominator is so I can compare them. The degree of the numerator, because I'm multiplying two things with just an x to the first in them, the degree of the numerator is going to be 2 if I multiply this out. Notice how I'm multiplying 3 linear terms in my denominator. So the degree of the denominator will be 3. Now if one of these was squared, for instance, that would obviously increase the degree of the numerator or the denominator, depending on where that was, right? Because that'd be like multiplying by it multiple times. Now the degree of the numerator is less than the degree of the denominator. So there is a horizontal asymptote at y equals 0 here. That one was easy enough. And now I want to find the vertical asymptotes. This is just where my denominator is equal to 0. So for vertical asymptotes, let's see, I have x minus 1 times x plus 2 times x minus 5. Set these equal to 0. And I get, this is where x is 1, negative 2, and positive 5. I have 3 vertical asymptotes here. Awesome. Let's move on. Find the vertical and the horizontal asymptotes of this function. Okay, so let's go ahead and find the horizontal asymptotes. I'm going to abbreviate this as HA. Notice that the degree of the numerator is 2. The degree of the denominator is also 2. And notice that the numerator, whenever I multiply this out, I'm going to multiply 2x times 2x. I'm going to have 4x squared up there, right? So my horizontal asymptote here is going to be the ratio of my leading coefficients. Maybe I should multiply this out just for clarity. Okay, yeah, we'll multiply this out just for clarity. 2x times 2x plus 1, so you can see what I'm doing here. And how I determined what the leading coefficients were. Whenever I multiply all of this out, I get, now I'm multiplying all of this out so I can find those leading coefficients nice and easily. The numerator becomes 4x squared plus 2x minus 2x minus 1 This is all over x squared plus 3x minus 2x minus 6. The numerator simplifies to just 4x squared minus 1. The denominator simplifies to x squared plus x minus 6. So my horizontal asymptote here, notice how I have degree 2 in the numerator and degree 2 in the denominator. My horizontal asymptote, because these degrees are the same, is the ratio of the leading coefficients. The leading coefficient of the numerator is 4. The leading coefficient of the denominator is 1. So my horizontal asymptote is at y equals 4 divided by 1, which is just 4. Going back up. Oh, I didn't mean to copy and paste it right up there. I'm trying to drag this problem down here where I have more space. OneNote does not want me to do that. Okay. There we go. Perfect. I now need to find the vertical asymptotes here. The vertical asymptotes here, let's see, the VA. These occur where x minus 2 times x plus 3 is equal to 0. So these are just going to be where x is 2 and where x is negative 3. And that's it. Perfect. And let's see. Oh yeah, of course we can find intercepts for these functions as well, right? A rational function will have a vertical intercept where my input is 0, if the function is defined there. And a rational function will have horizontal intercepts at inputs that cause the output to be 0, unless that input corresponds to a hole. So we find our intercepts just by seeing, let's see, okay. First of all, does anything cancel? If anything cancels, then I'm not going to have an intercept at that point. I'm going to have a hole instead. Well, we've actually seen this problem already. Nothing cancels here. So let's find our vertical intercept. There's only one of them. I get my vertical intercept by evaluating the function at 0. So I plug 0 in, I find f of 0. This is 0 minus 2 times 0 plus 3, all over 0 minus 1 times 0 plus 2 times 0 minus 5. This is negative 6 divided by positive 10, which simplifies to negative 3/5. This is my vertical intercept. Likewise, if I want to find my horizontal intercepts, or my x-intercepts, in this case, I only need to set the numerator equal to 0, because the function can only be 0 where the numerator is equal to 0. So for the horizontal intercepts, I just set the numerator equal to 0. So I have x minus 2 times x plus 3 equals 0. My horizontal intercepts are really easy to find here. They're just x equals 2 and x equals negative 3. Sketch this graph. I think I did not plot this one. Okay, I suppose, so this is very easy to graph, but let's just discuss what this will look like without necessarily graphing it, unless I have a graph somewhere over here. I don't have a graph of this. So instead of maybe sketching the graph here, we're going to describe what the graph will look like here. So let's notice that, let's see, does anything cancel? Nothing cancels here. I can find some intercepts and asymptotes. And this gets me a pretty good idea of what the graph of this will look like. Give me just a second. So, okay. So let's find my vertical intercept. So again, we're not going to sketch this, but we're going to describe. So my vertical intercept, this is where I plug in 0. And one reason why we're not going to sketch this is because things are so easy to graph using graphing software. Right? And I typically have these graphs prepared in this OneNote, but I guess I didn't have this one prepared this time, unfortunately. So, although, wait a second, maybe I think I can get the graph of this. Okay, maybe we can. Now let's just go along with this. We can look at the graph of this once we're done describing it. So once I plug in 0 here, what do I get? I get -6 divided by -2. This is +3. Looking at my numerator here and setting it equal to 0. So for my horizontal I can find my horizontal intercepts. So this is x plus 2 times x minus 3 equals 0. So my horizontal intercepts are x equals -2 and x equals +3. I can find my asymptotes very easily. Let's see, the degree of the numerator is 2. Degree of the denominator is 3 because I have x plus 1 quantity squared times x minus 2. So I'm really multiplying 3 things in my denominator here. So I have a horizontal asymptote at x equals or rather at y equals 0. And I'm going to have vertical asymptotes at what? X equals -1 and at x equals 2. We're going to see that once I graph this, at this vertical asymptote of x equals -1, or I guess near it, I should say, the graph is going to be heading, both branches of the graph that are approaching that x value will be heading in the same direction. They're both going to be going towards positive infinity here. Whereas at this other asymptote, the branches of at x equals 2, the branches of the graph are going to be headed in opposite directions. This is due to the power on the factor that gives us this asymptote. If I have an even power, the branches of the graph near the asymptote are going to be heading in the same direction. If I have an odd power on that factor, the branches of the graph near that asymptote are going to be heading in opposite directions on either side of the asymptote. And magic, just like that, this is what the graph of this function looks like. So I actually went ahead and I plotted this, and I grabbed all of these intercepts to show us that our intercepts were correct. Notice that once again, At x equals -1, both branches of this graph are heading in the same direction. And towards x equals +2, the branches of this graph are heading in opposite directions. Let's look at the last topic here. Perhaps I'll start one more video.